finite subgroup.
real line is
Okay. Again, this is. Thanks for asking this question. Actually, thanks for asking this question. Definition of compact sets, that for every cover you must have a finite subcover, and we tend to forget this early. We tend to forget this early. So when you are when you want to prove something is not compact, then you have to show that there is a cover for which no finite subcover. And now I say that weight your question yourself, because even if you cover it with a small interval, open interval, but then that would be just one cover actually. While for the compactness you have to show that take an arbitrary cover. So if there are 10,000 covers for which you have, what do you call, finite open subcovers actually. But there is a one cover for which you don't have finite open cover, that set is not compact. Are you getting the point? So since that collection, that O alphas that we were taking was an arbitrary collection, so we need to prove this basically, that closed interval A to B, for every arbitrary open cover for the closed interval A to B, we have a finite subcover. So this arbitrariness will be missing if you choose one particular cover. Okay. So these things are important. Take care of it. I'm defining a kind of compactness. It's called sequential compactness. Last two results. Sequential compactness. So what do we mean by it? Something be sequentially compact. So a subset K of R, is sequentially compact if every, and again this every is important, don't forget, every sequence xn in K, every sequence, no restriction. In K means all of these terms belongs to K. Okay, so every sequence in K as a convergent subsequence. Okay. So K is a kind of a set in which every sequence has convergent subsequence. Alright?
Only one or at least one?
What do you mean?
A sequence, at least one subsequence or?
Yes, at least one subsequence. There's at least one subsequence. In other words, for a sequence, for a set, you want to show that something is not sequentially compact show that you take any sequence in that set and it has, no convergent subsequence. For example, I'll give you the two examples. For example, I say take k equal to say 0, this 1 half, maybe 1 half, 1/3, and so on and so forth, and this is 0, something like that. Okay. Is this sequentially compact? So what do we mean by that? So can I take some sequence from here? So if I take any sequence from here, how does it going to look like? So any sequence, okay, is going to be of this form actually. Okay, this form. Are you getting the point? Maybe 2n or 3n or something like that. It's going to be of this form. Are you getting the point? And we know that such sequences converge, and hence their every subsequence converge actually. Are you getting the point? It will be a bit extreme case, but this set is sequentially compact. So you pick any terms out of this sequence, okay, this set, okay, and create a sequence. That sequence would also always have a convergent subsequence. In fact, that sequence itself is going to be convergent. Okay. So that is sequentially compact. How about set of natural numbers? So it's like 1, 2, 3, and so on and so forth.
No.
Is this sequentially compact? Think about it. Take any sequence out of it. How does the sequence is going to look like? So it could be like n square plus 1, n raised to n, 2 and so on and so forth. So the sequences are going to look like this actually. Okay. So does all of these sequences converge? Does these sequences have any convergent subsequence? No. This is not sequentially compact. Are you getting the point? Okay. So the sequential compact is, compact means that. So here's an interesting thing. We observed that this is also compact actually. I mean, last time we talked about this example and we showed that no, this is compact. And interestingly, it's also sequentially compact. So the natural question arises, is there a relationship between compactness and sequential compactness? And the answer is yes actually. That in R, they both are equivalent. In other words, there is no difference between compactness and sequentially compactness. So if a set is compact, it's sequentially compact. If the set is sequentially compact, it's compact. But in arbitrary metric spaces and arbitrary topological spaces, this is not the case actually. Okay? In arbitrary topological spaces, you can have spaces for which, a set is sequentially compact but not compact. Okay? So 2 examples, and I'd like to quickly just a quick result. It's going to take too much time because we have done the hard work already. So it's going to be just one-liner proofs. Okay. So K subset of R is compact if and only if K is sequentially compact. Okay, so compactness is same as sequentially compactness in R and in Rn, obviously, but not in general. What would be the good thing coming out of this result? So the good thing coming out of this result is that now for the compactness, you know the 2 criteria actually. One that, okay, can I check that it's closed and bounded? Okay. So sometimes it's not that easy to basically check that whether something is closed and bounded or not. Okay. But the other thing is, can you just check that it's sequentially compact? In other words, does that set contains the sequences and those sequences has further convergent subsequences or not? So it's like breaking down compactness in the terms of the sequences actually, which are easy to deal at. We know sequences, it's really easy to create sequences actually. Okay? Not always, but sometimes. Okay? So let's quickly prove this. Let's see that why this is true. This will be the last result for today's discussion in this chapter.
सीक्वेंशियली कॉम्पैक्ट में लिमिट सर उसकी उसी सेट में मौजूद होनी चाहिए या सर सिर्फ कन्वर्ज?
Okay, this is a very good point.
अगर सर लिमिट नहीं होगी तो फिर
Convergent subsequence. This is a very good point. Converging in K. Okay. What do you mean by converging in K? That the limit should belong to. So if I write it mathematically, how does it going to look like? That for all such sequences in K, there exists some xn K, okay, such that xn K converges to some x in K. This is what sequential compactness. It's like a more precise way of putting it. As n goes to infinity, obviously. Let's try to prove what we want. Let's see this thing out. Okay? What does it mean? Suppose K is bounded. Suppose K is bounded. Now it says K is compact. Compact. Obviously it's closed and bounded. Okay? And take a sequence xn in K. Xn in K means that xn belongs to K for all n in n actually. This is what that xn in K means. When I'm saying that I want to take a sequence in K, so it's like all terms of the sequence belongs to K. Give me a reason that why this must have a convergent subsequence. So since K is compact, so it must be bounded. Okay. Bounded means that every single element of this set K is smaller than, or its absolute is smaller than some m. Okay. And as every single K element of this K is smaller than some number, fixed number r, so in particular this sequence would be also smaller than that number, and hence that sequence would be, this sequence would be bounded actually. And you have a result which is called Bolzano-Weierstrass theorem, which says that for every bounded sequence there exists a convergent subsequence. This is a line of argumentation. Do I need to write it? Okay, let's quickly write it. K is compact, so K is bounded. exist some r positive such that x is less than r for all x in K. In particular, xn is less than r. Okay? For all n in n. This implies xn is bounded. Okay? So by Bolzano-Weierstrass theorem, there exists a convergent subsequence. But there will be one more. There exists a convergent subsequence xmk of xn. Okay? Alright? Is it necessary that this sequence must converge to K? Must converge inside K. Bolzano-Weierstrass theorem is not telling us that it should converge inside Z. They just tell us for a sequence there must be a convergent subsequence. It doesn't tell us. So xn, say xn k converges to some x as k goes to infinity. Okay? But since k is compact, so it's closed actually. So we know a theorem about closed set, that in a closed set, if you take a convergent sequence, its limit should also belong to K. Also, since K is closed, so see, you see that both things are playing a pivotal role, boundedness and closedness. So boundedness is proving that okay, such a sequence exists, and closedness is making sure that the limit is going inside. Since K is closed, so the x belongs to K actually. And simply is the proof of one side. I know we have done lots of theoretical things. These things are important. In practical sense, they are going to make our life easy. Okay. What would be next thing to show? Let's see. The next thing to show. So, what does this show? That compactness implies sequential compactness. Now, I want to show quickly that sequential compactness implies compactness. And what's the meaning of sequential compactness? Every sequence has a convergent subsequence inside. This was that. I want to show that K is compact. And for the compactness, I'm going to show that it's bounded and closed. Okay? So I'm saying, suppose K is not bounded. Suppose K is not bounded. In other words, give me any number, I'll give you an element in K which is going to cross that number actually, which is going to be bigger than that number. Okay? Now for every n in n, okay, there exists an element, okay, there exists some element in K, okay, such that that element goes beyond that n actually. Because this is what the definition of boundedness is. I'm giving this element a name xn. So for every n I'm going to find. Okay. Now if this is true, what does it tell us about the sequence? This shows that the sequence is unbounded. Okay. The sequence is unbounded. And this implies xn is unbounded, and so possible subsequential limits are going to be plus minus infinity. Okay? Plus minus infinity. But does plus minus infinity belongs to the K? So it's kind of contradict your definition of being sequential compact. Hence, K must be bounded. Okay? So K must be bounded. For closed, so we know the criteria for closeness. What are the criteria for closeness? We said that if a sequence is converging, if you take a convergent sequence in closed set, then it must converge inside the set actually. In other words, if a sequence is converging, the sequence in K is converging to something X, then that X must belong to K actually. So to show K is closed, let's take a sequence xn, okay, such that xn converges to some L as n goes to infinity. As n goes to infinity. Okay. Are you getting the point? Now let's exercise the sequential compactness. What is the sequential compactness is going to tell you? It's going to tell you that this sequence has a convergent subsequence. But that convergent subsequence is going to converge to what? The same L actually, because the parent sequence is converging. We know that if a sequence is converging to some limit, then every single subsequence is also going to converge to some, subsequence. So I'm going to say by sequential compactness that exists in subsequence xnk such that this xnk is convergent. There exists convergent xnk such that it must converge to L. Okay, and we know that that subsequence which is convergent, its limit also belongs to K actually. So this implies by definition that this L must be in K, and this is what that you need to show actually. What was the definition of closeness? Closeness says that take a convergent sequence, its limit should also belong to K. And I'm saying that it follows from sequential compactness, that, by sequential compactness, there exists a convergent subsequence, but since this is convergent, so its subsequence is also going to converge to L, and this L is also going to be in K, and hence not only the limit of subsequence, but the limit of sequence is going to be in the K.
सर हम कहते हैं अगर -1 से 2 तक हम एक इंटरवल ले लिया, ओपन इंटरवल, अब इसमें हम 1/n सीक्वेंस लेते हैं, वो इसी को ही सर उसी में ही कन्वर्ज कर रही है, यानी लिमिट पॉइंट उसकी उसी से
नहीं
सर उसी में
वो कन्वर्ज 0 होगा।
हाँ सर, लेकिन 0 तो -1 से लेके 2 में सर आएगा, तो ये तो ओपन तो नहीं है।
Okay, shall I complete this proof? Okay, and then we will talk about it. So we have done. This implies that K is closed actually. So if K is closed and bounded, it must be compact. Okay. Did you understood this argument? Most of the people, you can discuss.